Hello maths fans! Dr Tom Crawford here at the University of Oxford, and today we are looking at the maths of the solar system. This video is a continuation of the Maths on Tour series, which began with my recent video on the maths of ancient Egypt. This time we're heading to Jaipur, India. Jaipur is a city full of historical and cultural sites, from the famous Amber Fort with its breathtaking mirror palace, to the royal crematorium grounds and the beautiful Mughal architecture. And whilst these are undoubtedly fantastic monuments which are well worth a visit, I am in Jaipur to talk about maths, specifically the maths of the solar system. Welcome to Jantar Mantar, an astronomical observation site built in the early 19th century and now a UNESCO World Heritage Site. There are a total of 20 main instruments which were constructed on the orders of the Mughal prince Jai Singh II to allow for observations of astronomical positions with the naked eye. The observatory forms part of a tradition of Ptolemaic positional astronomy which was developed in the 2nd century and remained in use for over 1500 years. Jantar Mantar played a leading role in the completion of the astronomical tables of Jai, used to determine the positions of celestial objects. The measurements taken by Jai Singh II form the Jai-e-Muhammad Shahi, which was used in India for over a century. The largest instrument is the Vrihat Samrat Yantra, the world's largest sundial, which measures time in intervals of 2 seconds using shadows cast by sunlight. There are several other smaller sundials which are aligned with the exact time in Jaipur and thus have to be adjusted slightly to align with India Standard Time. The amount of adjustment changes throughout the year but was 35 minutes on the day of my visit. Other instruments were designed to be used for predicting eclipses, tracking the locations of major stars as the Earth orbits around the Sun, ascertaining the declinations of the planets, which is the angle they reside from true north, and determining the positions and velocities of celestial bodies. The Ptolemaic system on which the observatory is based is an example of a geocentric model, which means the sun, moon, stars and planets all orbit around the Earth. It was developed by Ptolemy in the 2nd century and used until the late 16th century, where it was superseded by the heliocentric model, which places the sun at the centre of our solar system. The notion that the Earth revolves around the sun had in fact been proposed as early as the 3rd century BC by Aristarchus of Samos. The original text has unfortunately been lost, but is referenced by Archimedes as follows. His hypotheses are that the fixed stars and the sun remain unmoved, that the Earth revolves about the sun on the circumference of a circle, the sun lying in the middle of the orbit. Unfortunately, his theory didn't gain any traction until the work of Copernicus, Galileo and Kepler in the 15th and 16th centuries, who developed the model that we now use today. Aristarchus also made calculations on the relative sizes of the Sun, Earth and the Moon, as well as their distances from the Earth in terms of the Earth's radius. The calculations can be seen in a 10th century Greek copy of his original work on the sizes and distances of the Sun and Moon, and is in fact the only copy of his written work that's still in existence. So, how did he do it? And how accurate were the estimates? It's time to do some maths. The first calculation of the relative distances between the Earth, the Sun and the Moon is reasonably simple and uses the idea that at a half moon, the Moon forms a right angle with the Sun and the Earth. The setup is as follows. We have the Sun, which is of course the largest of these three celestial bodies. We then have the Moon, which is going to be at a half moon, so it's over here, and then we have the Earth, which is going to be down here. So this of course is very much not to scale, and we create a right angled triangle. So again, this works because we are at a half moon scenario. So this is at half moon. Now, we're going to label some of the angles and distances on the diagram. So we're going to call this angle phi. This one is the moon up here. Then we have the sun, which is the largest over here. And then this one, of course, is the earth. So the angle phi is the angle between the earth and the sun at a half moon. And then we're going to label the distance from the earth to the moon. That will be a distance labeled L. And then the distance from the earth to the sun, we're going to label capital S. So this is the geometrical setup at a half moon, and this is where Aristarchus's calculations began. He then measured this angle phi, and he believed that phi was equal to 87 degrees based on observations at the time and the equipment, let's say, that he had available. Of course, it's several thousands of years before we get telescopes, for example. But nonetheless, he has a value of 87 degrees. So using simple trigonometry, we can say, what have we got? We've got the right angle, we've got these two, we've got the hypotenuse and the adjacent, so that's a cosine. So we can say using trigonometry, which again, of course, wasn't available to Aristarchus, but nonetheless, the cosine of 87 degrees is equal to adjacent over hypotenuse, so the distance from the Earth to the Moon, L, over the distance from the Earth to the Sun, S. Now, as I said, trigonometry wasn't around yet, so Aristarchus had to estimate this value, and he did this using a geometrical analysis similar to those used by Euclid. So most of Euclid's earlier work was related to geometry and properties of triangles and what we would now call trigonometry, but of course he didn't quite phrase it or have those tools available. So the value that he was able to come up with was to say that cosine of 87 degrees he believed was between 1 over 18 is less than L over S, which itself is less than 1 over 20. Now it turns out that this is actually very accurate because I of course can enter cosine of 87 degrees into a calculator and it is approximately 1 over 19. So halfway between these two bounds. So what does this mean? What does this mean based on the calculations of Aristarchus? Well, L is the distance from the Earth to the Moon, and S is the distance from the Earth to the Sun. So this is telling you that the distance from the Earth to the Sun is approximately 19 times larger than the distance from the Earth to the Moon. So the Sun is 19 or 20 times further away from the Earth than the Moon is. So that's his first conclusion, that the Sun is approximately 19 times further away from the Earth than the Moon is. Further away than the Moon. Now the second important observation or important deduction that Aristarchus made based on this calculation is the relative sizes of the Sun and the Moon. Now, it was known at the time, and he himself observed, that the Sun and the Moon take up the same amount of space in the sky. So this, for example, is why eclipses actually occur. You need, of course, the Sun and the Moon to line up, but the reason that when they do, the Sun is blocked is precisely because they basically take up the same amount of space in the sky. And this was known back in ancient Greece. So if they appear to be the same size, but yet the Sun is 19 times further away, then correctly, at least based on these numbers, Aristarchus concluded that the Sun must be 19 times bigger than the Moon. But how do the sizes of the Sun and the Moon relate to the size of the Earth? This was the second part of his calculations and his contribution. And in order to work out that, we're going to need a second diagram showing the alignment of the sun, the earth, and the moon at a lunar eclipse. Now this one is a little bit harder to draw, so bear with me, but the idea is as follows. We have a lunar eclipse, which means the moon is the opposite side of the earth to the sun. So we imagine there is some point, unknown point over here, which is going to bound the earth and the sun. So again, this is very much not to scale. What we have is going to be the rather large sun over here, and this is going to bound it nicely. So this one is the sun. Then the earth is next. So again, definitely not to scale. Cannot emphasize that enough. The earth, let's say, is here and is bounded very nicely by this point. So that the fact that it touches both of them determines the location of that point. And then we actually have the moon. So this is the earth, sorry, earth. And then we have the moon, which would not be perfectly bounded by these lines, but is somewhere kind of hovering in here. Okay, so there is a gap between the moon and the kind of triangle shape that I've drawn, but not for the earth and the sun. And of course, geometrically, we can do that. So we have this. This is the lunar eclipse because the earth is sort of perfectly blocking the sunlight from reaching the moon. Now, we need to add some labels. And this is where things get a little bit complicated, so again, bear with me. Let's use a different color. Let's go with red. So we've got the center of the sun to the edge. So this is going to give us the radius of the sun, and therefore we're going to label the radius of the sun as r subscript s, radius sun. We're also interested in the radius of the earth, so we will label this one r subscript e, and as you may have guessed, the radius of the moon, so we'll label this one, I'll write it here, r subscript m. So we now have labels for the three radii. We again want to use what we've done over here, so we want to talk about L and S. So remember, we know that the Earth to the moon was the distance L, and then the Earth to the sun was what we called the distance S. So that adds those. And then the other thing that's going to be important here is going to be this distance. So from the center of the moon to the edge of the shadow of the Earth. So I'm going to label this D, and that is the distance from the center of the moon to the edge of the Earth's shadow. Now, as you may have guessed, we are going to do some geometry and we're going to do some work involving similar triangles. But before I draw those triangles, there's actually one further label or measurement that I need to add to the diagram. Now, this is going to be labeled D, and it's going to go from the center of the Earth here to this vanishing point over here. So this is an unknown distance, which we will label capital D. We could calculate it if we really wanted to know it. Turns out we don't need to know it. It's going to be eliminated from the problem at a later stage. But for the purposes of the geometry and the similar triangle approach, we're going to need to know this value, or at least have a label for it, a name for it. So, given this, we are going to consider two sets of similar triangles. Now, the first set focuses on the Earth. So, we're going to look at this right-angled triangle up here. And I'll draw it out to make it clear. So what we've got is the following. Have a triangle like so. We have a right angle. This is the Earth's radius. So here, this RE. And we have a distance all the way to the vanishing point, which is D. This is some unknown angle, let's call it theta. It doesn't really matter what it is, because then we know that this up here is 90 minus theta. Now, of course, partway through this triangle, we pass through the moon. So we're going to add that to our diagram because that's important, because at the moon here, we then know the distance between these two, we know is L. So that is L between the Earth and the moon. And then we also know this height, which I've labeled as lowercase d. Now, similar triangle bit. I'm going to draw a second triangle, which I'll do in red, and it's going to go above, sort of here. Make it accurate. So I'm drawing a second triangle here in red. Now, we have a right angle. We have here theta, and so this one is 90 minus theta. So you can see similar triangles, same angles. Now we know this horizontal distance, this is L, which is why I have drawn the triangle as I have. And then the height is the total height, RE, minus this distance d. So this is the radius minus d. So what we want to do now is look at the ratio of their side lengths. So if we take the long side of our bottom green triangle, we've got d over the shorter side, RE. So the bottom one over the vertical one. And then we do the same for the red triangle. So that's L is the horizontal distance divided by RE minus d. And they, of course, have to be equal because of similar triangles, which means the sides are in the same ratio as if the triangle was just being enlarged. So this gives us our first equation involving this unknown distance d, but as you can see, it involves the Earth's radius, involves the distance from the Earth to the moon, which is L, which we have some knowledge of over here, at least in comparison to the sun. And then we have this d, which is this kind of annoying thing involving shadows and distances. But we'll deal with that later. This is our first ratio and our first equation. To get the second equation, we're going to draw a second diagram and a second set of similar triangles. And as you may have guessed, this one will involve the sun and the big triangle here. So, using the same colors, we now focus on the sun. And what we want to do is draw the big triangle, which is going to, according to my diagram, look the same size. There's a right angle. Here, again, we have this angle theta. And again, we know that this one, therefore, is 90 minus theta. Now, distances. So we know we're going to go along to the Earth because we want to introduce S. S is something we have knowledge of over here. So we want to kind of stop partway through, like we did in the first case, but we want to stop at the Earth. So this one, we then know that this bit here is S, and then we know the height is the radius of the Earth. So this is RE. And then we know the distance from the Earth to the end is d. So we know that this bit there is d. So the total is S plus d across the whole thing. And then we also know this height, don't we? This is RS. Now for the second triangle, which again, I will draw in red, across the top, we follow the same pattern. We draw it to here, and we add labels. Right angle, we know this one is theta, which means that is 90 minus theta. We, of course, also know that this one is a right angle, and therefore this one is 90 minus theta. So we've actually got three potential triangles, and the reason I've added the second one, and I'll highlight this in blue, another color, this one here is the triangle I'm going to use. So this in blue is actually going to be the triangle that is similar to the red one. So for the blue triangle, we know the height is RE, we know the horizontal distance is d, and so we can take those ratios. So we're going to say Again, for the blue triangle, d divided by re. So the horizontal, the base, divided by the height is a ratio. And we want to do the same for the red one, which of course has the same angles, therefore similar triangles. So here, what do we know about the height? We know that's rs minus re is the height, so that's got to be the denominator. And then the distance across here is, of course, s, that part there. So that's s. So now we have these two equations involving the same ratio, d divided by the Earth's radius. D is unknown, but of course we can do one equation divided by the other, and then we've eliminated capital D, and we hopefully have an equation that we can work with. And again, this follows the same steps. We can't be sure it was the same calculation, but it follows the same steps, the same measurements that was done by Aristarchus. So taking our equations and doing the algebra in the center of the board, just about squeeze it in, hopefully. This one divided by this one, so I'm going to get L over this divided by S over rs minus re. So that's going to give me an L over an S, and then you're going to end up with, on the other side, an re minus d divided by rs minus re. So I think you're going to get L over S is equal to re minus d on the top divided by rs minus re. So this gives us a ratio here, L and S, which remember we have a bound for from Aristarchus' first calculation. And now we've got this kind of slightly complicated fraction involving different radius of the Earth and the Sun. Now at this stage, we're going to do something very clever, which is going to help with our calculation. And this is related to the kind of second thing that Aristarchus deduced from this calculation. So because the sun and the moon take up the same area of the sky, then what that means, and where can I squeeze this in? Let's put it down here. So if I put a star here, so because they take up the same area of the sky, we can say the ratio L over S, so the distance to the moon over the distance to the sun, is approximately equal to the radius of the moon divided by the radius of the sun. So this follows from this kind of second deduction that Aristarchus made in this calculation. And this is going to be helpful because it brings in radius and therefore the relative size of all of our objects. Because that's kind of what's missing here. We don't have an RM. And we're hoping to get a conclusion about the size of all three things relative to one another. So this is the neat part. We're going to basically make this substitution. So we're going to get now Rm with the moon over the sun is equal to the Earth's radius minus d divided by the sun's radius minus the Earth's radius. Now it's time to do some algebra. So I'm going to, and this of course could be done in any order, but what I'm going to do is multiply up and then take the Rm across. So doing that, I'm going to put that one up and then that one down. So I'm going to get an Rs minus Re, all divided by Rs. So I'm going to lose an Rs term. So I'm going to get a 1 from that one on top, minus an Re Earth's radius over sun radius, which is good because this is one of the things we're trying to deduce. Again, relative size of sun and moon compared to the Earth. That is what Aristarchus was able to compute. And then on the other side, we're going to get Re over Rm. So again, that's what we want. The relative size of the Earth and the moon minus d over Rm. So, the number one, we like. The ratio of the Earth and the Sun, we like. We're interested in that. The ratio of the Earth and the Moon, we like. We're interested in that. This is kind of annoying. This is the size of the Earth's shadow divided by the radius of the moon. So distance from the center of the moon to the edge of the Earth's shadow is d, and as you can see here, there's a radius of the moon which is smaller than it. So this is this kind of ratio of these two things. But we'll come back to that in just a moment, because what we can get from this is actually going to be a couple of expressions specifically for these two ratios. Let's first look at the moon. So we want to make this the subject of the equation. So what we're going to do is add d over rm to both sides and then add re over rs to both sides. So that's going to give us an re over an rm, and then what we're going to do is write that as a 1 plus. Now we've got this term added to it. So we've already got the re on the top, but we've pulled out an rm, so we have to add it back in so they cancel, and then we get the rs on the bottom. And that is going to be equal to what's left, which is going to be the 1 plus d over rm. So what this means is that we can actually express the ratio of the Earth and the Moon in terms of the ratio of the Moon and the Sun and this kind of d Moon Earth shadow annoying parameter. So putting it all together, we can say that re over rm, which is what we want, remember, is equal to 1 plus d over rm divided by 1 plus the ratio of the moon and the sun. And that right there is going to be our first equation. And then going back and doing something almost identical, but this time we want to make re over rs the subject of the equation. So you're going to do almost identical calculation, and you're going to get re over rs. Then you would, going sort of step by step, you'd have 1 plus, and then you've got this factor. So you would need to do an rs over an rm. So kind of this one, but flipped. And then you're going to divide by that. So the numerator is the same, but what you've got on the denominator is going to be a 1 plus rs over rm. So just to make it really clear that these two equations are extremely similar, what we're going to do is pull out the rs over rm factor and then write it as a 1 plus rm over rs. So anyway, you can fill in the details for yourself. It's just simple algebra, but you're going to end up with the same factor, the 1 plus rm over rs on the bottom, but then you just have this additional factor out here, which is going to be rs over rm. And this is going to be our second equation, which is very similar to the first. The top one gives you the ratio of the Earth's radius to the Moon's radius, and it's in terms of two parameters, which we'll talk about in a moment. And the bottom one gives you the ratio of the Earth's radius and the Sun's radius, again in terms of the same two parameters. Have this additional thing here, but this is just the inverse of the one inside that. So to sort of summarize, the two things we want can be given by these two equations, provided we know these two things. And it just so happens these two things were measurable observables both today and back in the time of Aristarchus. So what are the values? Well, this one, rm, rs, and some of you may have spotted this, we've got that over here. So over here, from this sort of first calculation of Aristarchus, we said that the ratio of the moon and the sun is the same as the distance, the ratio of their distances, and we have, at least Aristarchus had, an estimate that that was 1 over 19. So we know rm over rs. So taking rm over rs to be Aristarchus's value, we think that is 1/19. So that goes straight into here and straight into here, and then we have this one as well. That's of course 19. And then the other thing we're missing is this. Now, as shown in the diagram, this is the ratio of the distance from the center of the moon to the edge of the Earth's shadow divided by the distance from the center of the moon to the edge, so the moon's radius. And this was measurable, was observable in ancient Greece. Again, several thousand years before telescopes, so it wasn't the most accurate measurement, but nonetheless, they had a value, Aristarchus had a value of 2. So, and this is, I guess, measurable by observing the shadow cast by the Earth as it crosses the moon. That's how you would do it. Lots of very nice stuff that I found online explaining how you could do this today with a telescope in your own back garden, so I'll link that in the video description. But I don't want to go through that because that's probably a whole other video in and of itself. So I will just say it is possible. Aristarchus had the value, which was 2. So, using his values, we've got that one, and we've got d over Rm is 2. So substituting those into our equations, we're going to get the answers. So Re over Rm, the ratio of the size of the Earth compared to the radius of the moon, is 1 plus that, so that's 3, 1 plus 2, divided by 1 plus 119. So that's 20 over 19. So that's going to give me, on the top, 3 times 19, that's going to give me 57 over 20, yes, which is approximately 2.85. Now, those of you who know your celestial body sizes and ratios and relevant sizes will know that the Earth is more than 2.85 times bigger than the moon. But given this was before telescopes, it's not actually that bad. So this gives you 2.85, and the actual value, which I'll put in brackets, is 3.7 approximately. So again, given how long ago this calculation was done, I think that's pretty good. Now the second one, perhaps less so, but anyway, we will calculate it nonetheless. The ratio of the Earth and the Sun, again, we're going to sub in the values. So we've got the values we need. So that means that Re over Rs, therefore, according to Aristarchus's numbers, is 3 divided by 1/19. So that gives me a 19 outside because I flip it. And then I've got 1 plus that, so that's then a 20 over 19. So I'm going to get 3/20. Now, this is actually easier to flip. So if you flip this, that will imply that the Sun over the Earth, so the Sun is therefore approximately 6.7 times bigger. According to Aristarchus, the Sun is 6.7 times bigger than the Earth. That is not true. That should, in fact, be 109. So that one is a lot more non-accurate, shall we say. That's a lot further away than the real value. It's not 6.7. The Sun is 109 times bigger than the Earth. But, you know, again, given the time period, it's not terrible. I'll talk more about this in a moment, but basically, you're out there because this bit is out. And there's actually a really interesting story and bit of history around what happened here, and possibly how the numbers used by Aristarchus maybe could have been misinterpreted. So as I mentioned, the answers here are off by quite a bit because of the accuracy of the measurements, right? It would be another 2,000 years before telescopes exist. So, you know, what do we expect? However, there is another plausible explanation related to a possible mistranslation of the work of Aristarchus. And of course, we cannot verify this because we don't have the original work. But nonetheless, I'll tell you the story. So Aristarchus describes in his work 1/15 of a meros of the zodiac. Now, this was interpreted or translated or assumed to mean 1/15 of a zodiac. A zodiac is 30 degrees. So 360 degrees gives you the full orbit. There are 12 zodiacs, so each one represents 30 degrees, as you might expect. So 1/15 of a meros of a zodiac, therefore, quite reasonably, could be assumed to mean 1/15 of a zodiac, which would therefore give you a measurement of 2 degrees, 1/15 of 30. And that's what was used here. Now you could also interpret meros or miros to mean a portion. And I believe that, again, according to Wikipedia, is a possible translation of that word. And a portion of the zodiac would actually be 7.5 degrees. So when you're taking 1/15 of a meros of a zodiac, you're taking 1/15 of 7.5, which is half a degree. So that is 4 times smaller than that original possible interpretation. So if you were to use that translation or interpretation, you would actually get a 4 times more accurate answer. It wouldn't be perfect, but it would give you more accuracy. Now, however, we are still some way off the modern values. And in fact, the sort of key to all of it, the bit that's really messing this whole thing up, goes right back to one of the first things I wrote on the board. And I'm going to circle this. This measurement of the angle phi. So this, as shown in the diagram up here, is the angle between the Earth and the Sun at the half moon. Now Aristarchus had this as 87 degrees. This is not anywhere near accurate enough, because that means that the Sun is only 19 times further away. It's actually about 400 times further away, and so they're out by quite a bit there. So this is the problem. Now, I don't know if this is coincidence, but I'm going to throw out my own hypothesis here, because the actual value you want here is 89.85 degrees. Would be much more accurate. Now, of course, I could add more decimal places and make that even more accurate, which is needed to get these distances, because we're dealing with very, very small changes in angles. However, the reason I'm going to use 89.85 degrees is Aristarchus mentioned 1/15. Now, again, this is complete hearsay on my part, but I think it's nice. Let's suppose that the 1/15 mentioned by Aristarchus was actually 15 parts of a degree. And if you take it to mean 15 parts of a degree, and we give him the benefit of the doubt, then that would mean that this angle was 15 parts of a degree less than 90, i.e. 89.85 degrees. So if I enter 89.85 degrees into my calculator, I calculate cosine of this. Instead of getting approximately 1/19, I now get approximately 1 divided by 382. So this, I can now say, is 1 divided by 382. Now, of course, you'll notice it's not the 1/400, and that's because I've slightly fudged this so it fits with the 15th. Again, this is just me having a bit of fun with numbers, but let's run with it. So if you go with this, because he mentioned 1/15, so we go with that as being 15 parts of a degree less, you get 1/382. So that means the Sun is 382 times further away from the Earth than the Moon. And then we can use this value over here in these formula. So we now get 383 over 382 down here, which basically comes out, this is now approximately 3. So it's an improvement on 2.85. It's close to the 3.7, but we are still off. And as you may have guessed, that's because this number is also not perfect. But anyway, he didn't mention that. So, and then the second one down the bottom, so we're a long way off there, being 6.7. But if you enter these numbers instead, so again, we're going to enter the, this one will now be 382 on the bottom, and then this is now 383 over the 382. Plugging all those numbers in, instead of getting 109 times bigger, sorry, the actual answer is 109. Instead of getting 6.7, we now get 128. So this comes out now to be approximately 128, which is much closer to that actual value of 109. Again, it's not perfect because this value is incorrect. And even this isn't perfect. But given the conditions Aristarchus was working in, given this was 2,000 years before telescopes existed, I personally, at least, am willing to give him the benefit of the doubt and say, this is actually what he meant. You know, he probably didn't, but it's a hypothesis. Suppose this is what he meant, and suddenly we've got much, much more accurate estimates for the relative sizes of the Earth and the Moon. So this is saying the Earth's about 3 times bigger than the Moon. It's actually 3.7. And it's saying that the Sun is about 128 times bigger than the Earth. It's actually about 109. But that is pretty good. This is pretty good. The whole thing is amazing. It's pre-telescope, so I, for one, am lending my support to Aristarchus. That does now bring us to the end of our journey into ancient astronomy, inspired by my visit to Jantar Mantar in Jaipur, India. I thought I would leave you all with one final sight from my trip, in the form of this beautiful stepwell, which is used to harvest and store rainwater during the monsoon season of Rajasthan. As with the majority of Mughal architecture, the use of geometry and mathematics shines through to create something incredibly aesthetically pleasing. Thank you as always for watching. Please do remember to subscribe to the channel if you've enjoyed this video and in particular would like to see more from the Maths on Tour series, and I'll be back very soon with some more maths fun. Take care.